Hi everyone, my name is Asheq and I'm going to talk about a least mode OECM based attenuation and scatter compensation method for SPECT. Quantitative SPECT has several applications such as developing imaging biomarkers and SPECT based dosimetry. For example, in dopamine transporter SPECT imaging, there has been interest in the uptakes in striatal region as a biomarker for measuring severity of Parkinson's disease. For these important clinical applications, there is a need for reliable quantification from SPECT images. However, due to attenuation and scatter of photons, quantification accuracy can be degraded. In SPECT imaging, a proportion of the emitted photons reach the detector without any scatter. Another set of photons are scattered within the tissue and are lost, leading to attenuation artifacts, or detected as scattered photon, leading to scatter artifacts. These attenuation and scatter artifacts affect quantification accuracy. Thus, there is an important need to compensate for these artifacts. Existing methods for attenuation and scatter compensation can be broadly categorized into two types, iterative and non-iterative. Iterative methods include approximate modeling of scatter kernel, as in convolution subtraction based methods or in ESSE. Analytical modeling includes Monte Carlo simulation or Klein-Machina-based modeling. Non-iterative attenuation and scatter compensation involves energy window-based methods such as dual energy window or triple energy window. However, these methods do not use the precise value of energy information that can be estimated in least mode acquisition. Prior work in PET showed improved accuracy when using energy information and least mode data. In our previous study, we showed that scattered photon outside the photopeak window contains information for estimating attenuation and activity distribution. Let us go through two different data models that exist in nuclear imaging. If we consider each detected photon as an event and save attributes of each event in a list, then this format is called least mode data. This format is crucial for photon processing systems. However, if we accumulate counts in a range of attribute values and represent it as a histogram style distribution, then the format is called bin representation. It is often referred to as sinogram. Several studies have shown that binning can lead to loss of information. Now let us give an intuition why scattered data and energy information in least mode can help improve quantification. The need for using scatter window data is mainly due to low sensitivity of SPECT acquisition. Extracting useful information from scatter window can help increase the sensitivity of the SPECT system. Moreover, the scattering location can be modeled using information of attenuation distribution, and the scattering angle can be modeled using Klein-Machina-based formula. As contour scattering is the dominant scattering phenomena, energy of detected photon also carries information about the scattering angle. Thus, adding energy information helps assign more accurate probabilities of a path the photon traverses. And if we save the data in least mode, it can provide us more precise value of energy than binned data. Based on this premise, we proposed a two-dimensional least mode reconstruction algorithm for SPECT that extends upon a previous study. The proposed method incorporates scattered events outside the photopeak window. It incorporates energy information of least mode events. It also performs attenuation and scatter compensation by modeling photon propagation using a radiative transport equation. And we also implemented an ordered subset approach for computational efficiency. Now to develop the maximum likelihood algorithm, we need to define the likelihood of least mode data. Consider a two-dimensional preset time SPECT system. As all events are independent, we can write the likelihood of least mode data as products of likelihood of each least mode event. In this equation, F denotes the activity distribution, J denotes the number of detected least mode events, AJ hat denotes attribute vectors, that can contain attributes such as energy, position, and acquisition angle. A represents the full least mode dataset. The first term in the likelihood equation denotes the probability of number of detected counts. It can be modeled using Poisson distribution. The second term denotes the probability of an event given the underlying activity distribution. Analytical modeling of this probability is difficult, so we use the fact that each event traverses a particular path before being detected. Thus, we can decompose this probability of event into probability that the event takes a particular path and weighted by probability of a path. The first term denotes probability of detection of an event taking a path, and it can be modeled using statistical properties of detector. The second term denotes probability of a path. It can be modeled by photon propagation using radiative transport equation. As path is now an unknown variable, expectation maximization provides an opportunity to maximize this likelihood. So we define a hidden variable z for each event and each path. Z equal to 1 if an event takes a particular path. So these hidden variables paired with observed least mode data forms the complete data. Likelihood of this complete data can be derived. For expectation maximization, we take the conditional expectation of this likelihood conditioned on observed data and maximize it with respect to activity distribution. Following this step, we can get the update equation as shown. In this equation, z bar denotes the conditional average of hidden variable. Intuitively, it represents probability that an event traverses a particular path. In the denominator of update equation, S sub EFF denotes the sensitivity of a path. For the updates of a qth voxel, paths that start from voxel q are considered. It is denoted by P sub q. The numerator contains sum of z bar over all the events and all paths that start from q. Thus, it denotes how many counts are detected due to emission from voxel q. Denominator contains total sensitivity of qth voxel to the system multiplied by acquisition time. Thus, intuitively, the right side of update equation refers to mean rate of emission from voxel q. However, for each iteration, we need to calculate z bar for all paths and all events and sum them up, which is computationally expensive. Thus, we implement an ordered subset approach. In ordered subset, at each iteration, we only used a subset of the detected events. We formed the subset of events based on the angles the events are acquired. For example, consider that our SPECT system acquires data from 8 angular positions. A total of 16 events are detected, denoted by E1 through E16. We assume for each angle we detected 2 events, and we want to divide the events into 4 subsets. The first subset can be formed using events that are detected at angular position 1 and 5. Using these events, we can perform an update and use it for next initialization. We can form the next subset using position 2 and 6, third subset using position 3 and 7, and fourth subset using position 4 and 8. After these 4 sub-iterations, each event is used exactly once for updates. This 4 sub-iteration then completes one main iteration of OSM algorithm. Then we can repeat this process for further updates. We evaluated our method in the context of a dopamine transporter SPECT imaging study. There is a significant interest in quantitative DAT SPECT imaging, and in particular in studying the uptake in the caudate and putamen regions for improving diagnosis and measuring severity in Parkinson's disease. The evaluation was conducted using a realistic simulation study, because in this study, the ground truth quantitative uptake in the various regions were known. For the simulation study, we used Zuval Phantom and assigned clinically relevant uptakes in caudate, putamen, globus pallidus, and background region. The least mode data was acquired using Monte Carlo simulation in a realistic SPECT model. The SPECT geometry was based on the Optima 640 parallel hole system. We modeled finite energy and position resolution of sodium iodide detector. We modeled the depth-dependent collimator response and the processes of attenuation, scatter, and detector noise. Using this system, the data was acquired from 120 viewing angles in least mode format. For each least mode event, we saved the position, energy, and detector angle. We set the scan time such that only 1/3 of the clinically accurate counts are detected to simulate a low-dose acquisition. We performed our proposed least mode OACM reconstruction method for 4 iterations and 4 sub-iterations. We evaluated our results based on the quantitative uptake in coded and putamen regions. As we mentioned earlier, this is a clinically relevant task as several studies are looking into whether these uptakes can help measure severity of Parkinson's disease. To measure the accuracy of quantification, we calculated the normalized root mean square error between true and estimated uptakes inside coded and putamen regions. We did not perform any partial volume compensation because we only wanted to see the effect of attenuation and scatter compensation. In the first set of experiment, we tried to observe the effect of including events from scatter window on quantitative accuracy. For this purpose, the reconstruction was performed in 3 different settings. First, least mode events from entire energy spectrum were used. Secondly, we used least mode events that have energy above 120 kV. And finally, we used least mode events that fall into photopeak window. The figure shows the normalized root mean square error in estimated activity uptake as a function of iterations in ordered subset expectation maximization algorithm. We observed that inclusion of data from scatter window results in lower root mean square error at each iteration. In all the cases, the root mean square error decreases as iteration progress. We then looked into the effect of binning in the quantitative performance. Least mode data from entire energy spectrum was used for this experiment. We binned the position and energy attributes of detected least mode events. The energy attribute was binned into 2 and 3 bins for 2 separate experiments. Events that fall into a particular energy bin were assigned a representative energy value of that bin. We observed that least mode data format leads to lower root mean square error for all iterations compared to binning the attributes. The reconstructed results from low-dose data showed improved visual quality when least mode data was used compared to binning the attributes. The images obtained using the least mode data appear less noisy. To conclude, the proposed attenuation and scatter compensation method demonstrated that processing data in least mode format and including scatter window data provides improved reliability in quantification tasks, and we evaluated this using a simulated dopamine transporter SPECT imaging. Finally, I would like to thank my collaborators, colleagues, and funding agencies for supporting this research. Thank you all for listening.